review and the final exam itself is only going to have superficial questions about Chapter 9. Okay, so we're focusing on the early chapters all the way up to 8. Any questions so far? All right. Your final exam, remember, is scheduled for Wednesday. That's the 14th. It'll be 10 o'clock. They're very unclear as to exactly where it will be. It'll either be there or here. So if it's not there, it'll be here. Okay, we can do that. The exam will have 40 questions. That's twice as many as usual. It's worth 200 points, and it has a 5-point extra credit.
Are they all multiple choice or?
Are they all multiple choice? No. There are probably 3 or 4 that are short answer. Okay, but most of them are multiple choice. The character of the exam should very closely parallel what we're talking about today. Yeah.
I have another exam, I guess, that's scheduled in the middle of this. How long should it take?
Oh, it would take me 15 minutes.
Okay, so like less than an hour.
It should be, right. If you have a problem, we can just work it out. Or if you like, you could come Friday for the other classes exams. So you decide.
Yeah.
All right. I hope you have the sheet. Let's just go through these. Again, they're fairly simple and straightforward. Remember all the way back in Chapter 1, we did properties. We did physical properties and chemical properties. Physical properties describe what things are like, what they look like, smell like, all that stuff. Very physical, physical state, etc. Chemical properties describe a chemical reaction. A chemical change is associated with chemical properties. A melting point, that's very physical. Atomic weight, again, that's a very physical phenomenon. Density, waxy solid, those are all physical. However, combustion in air, that's reacting with oxygen, that is a chemical reaction, therefore it's a chemical property. Mixtures, remember those. Mixture containing 2 compounds must be heterogeneous. Well, of course not. We remember we have 2 types of mixtures, homogeneous and heterogeneous. Compound may contain only 1 type of atom. Wow, that's a stupid compound. Called an element, isn't it? Pure substance must contain only 1 type of atom. That's a pretty boring substance. Heterogeneous mixture must contain at least 3 elements. That doesn't make sense either. And finally, homogeneous mixture is a mixture just like heterogeneous, except this is uniform throughout. Homogenized milk. Boy, I hope there's a lot of these, right? Which is copper?
CU.
CU. Remember when that was difficult? This is a little bit more difficult. Sulfur, selenium, silicon, strontium. Sulfur we know is an S. That's an easy one. So we can narrow it down to our bottom 3. Selenium. Selenium is going to be an Se, so we can narrow it down to those 2. This is 10, of course. Silicon. Well, all those are silicon. Comes down to strontium. Is that ST or SR?
SR.
It's SR, of course it is. What's nitrate? Remember, when you have the parent with all of the oxygens, it's an 8 when you take one away, the charge stays the same, but it becomes an ite. This is nitrate, and this, of course, would be nitrite. Silver 1 sulfide. Usually we don't have to indicate a oxidation number for silver, even though it's a transition metal, because silver is so reliably +1. What you have to remember here is, what is sulfide? Sulfide is right under oxygen, so it tries to be just like oxygen, a group 6 element, and it will be a -2. Therefore, we need 2 silvers for every oxygen, or sulfur, Ag2F. Group 6 element, -2 charge. What is the chemical name for this stuff? Well, CD. Is CD going to be calcium or cadmium? Cadmium, of course. Now, is this going to be hydrogen carbonite? Nope, remember carbonite was in Star Wars. It doesn't really exist. So it's going to be one of the carbonates. It's certainly not a bicarbonate. We need to say hydrogen carbonate. We have 2 of them. Each one is a -1, so this must be a cadmium 2. Now this one is interesting. It's not difficult, but you have to think just a little bit, okay? We have a compound that has 2 carbons, and that corresponds to 24% of the mass. This stuff is 100 grams per mole. All right, this is 24% carbon. Each one's going to weigh 12, right? So, let's say, excuse me, thank you. Let's say we have 100 grams of this stuff. That means out of our 100 grams, 24 of it is going to be carbon, right? So how much is this magical X? 100 minus 24, 76. Now there are 4 of them, aren't there?
Divided by 4.
76 divided by 4 is 19. This is fluorine. So a little bit of thinking, but not too difficult. 24 of it must be carbon, 76 must be our unknown, and we have 4 of them. Saccharin looks like this, C₂H₂O₂NS. This question was so very simple.
I think it's a.
What is its molar mass?
It is multiplied.
All you do is add them up, right?
Multiplied.
So we have 3 times 12. We have 5. We have 3 times 16, 14, and a 32. Add them all together, and it's 135. Molar mass, remember that means 135 grams of this stuff is 1 mole, 6.02 times 10 to the 23rd molecules. Novocain contains 2 nitrogens. I don't even tell you what it is because you don't need to know. It has 2 nitrogens though, and it has a mass of 232. What's the percentage of nitrogen? How do we do percentage? We take how much nitrogen we have over the whole thing, right? and then multiply by 100. We have 2 nitrogens at 14 each. So that's going to be 28 divided by 232. 2 times 14, 14 for each nitrogen, divide by 232, 12.1%. All right, this one is actually very, very simple. They gave us on an exam once, and lots of people missed it, which always astounds me when they're supposed to be so simple. Which of these contains the largest mass of hydrogen? Now, we're given different molar amounts and different formulas, right?
But you ask about hydrogen, so hydrogen will be.
All we have to do is figure out how many moles of hydrogen we have in each of these, right? So this is going to be 1.5 times 4. 1.1 times 9. 2
So D,
times 5.
D.
4 times 3. 1.1 times 8.
So D.
Now, which of these numbers is the largest?
It's like
12. Any questions on this? We have a liquid, and we have a volume. We have a mass. That means we can calculate a density. Remember, density is going to be mass divided by volume. And we have 3 unknowns here. We're trying to match it up. Our mass is 6.87 grams. Our volume is 7.8 milliliters. This is 0.879 grams per mil. And that just happens to match up here with benzene. Remember significant figures, I hope you do. I told you in class that we would have questions on just simple significant figures and on doing calculations with significant figures. First of all, this is simple scientific notation. Remember, in scientific notation, all of the digits in your coefficient are significant. This has 4 digits, therefore this has 4 significant figures. Let me pause for a moment while I remember something. It doesn't happen often. I remember something. Triton upgraded their blackboard. Okay? You would think that would be seamless, right? When you enter exponentials on the old blackboard, you would enter this as 4.030 e minus 6, right?
Yep.
Now you must use an uppercase.
Yeah, because I know some of them, when there was that voice, when you use the
So
long,
as you're doing these things, please make sure you
they will
remember
count it as one.
only the uppercase E works now. All right, I diverge. Here we're doing simple addition, and we want to know significant figures in our result. Remember, we have 2 rules, one for addition, subtraction, one for multiplication, division. For addition and subtraction, what you do is you look at the number of digits after the decimal. Here we have 2 digits after the decimal, but here we only have 1. Therefore, our result can only have one digit after the decimal point. So we add them together, we round it, 122.4. One digit after the decimal point. The other rule is multiplication and division.
The lowest number.
For that, you look for the significant figures in each of the numbers. Here we have 4 significant figures. Here we only have 2. That means our result must only have 2 significant figures. This one is even simpler. Which or how many of these have 4 significant figures?
4.
Well, the zeros here are in the middle, so they work. Here we have a decimal. That means the zeros are real. Of course, we ignore the leading stuff. This one's in between. All 4 of these are significant, and all 4 of these. We have 0.042349 meters. I want this rounded to 0.1 millimeters. Now what you want to do here is to look at this number and say, okay, how many millimeters is that? That's 1,000 millimeters in a meter, right? So what divide this by 1,000? We're up here, there's our decimal now, 42.349. We're going to round to the closest 0.1. So this thing should round to 0.2. You remember weighing crucibles in class. Well, here we weigh a crucible 5 times. And we're trying to figure out which person has the best answer. We're looking for the accuracy. So that means we're trying to be as close as we can to the real value. The actual value is 24.3162, whatever. What you want to do here is simply add all these up and divide by 5. You're looking for the average. Which student's average is closest to the real number? When you do that exercise, A is 24.3, B 24.4, or 24.8. A is closest. Student A passes the course. Now this one is designed to make people crazy. All right? We have 7.5 milliseconds. How many of these are also 7.5 milliseconds? And it really is designed to make you nuts, okay? Milli, remember, is 10 to the minus 3. What we're going to do here is simply add our exponents for all of these until we find one that hits 10 to the minus 3. We have micro. Micro is 10 to the minus 6. We add minus 3 and minus 6, that's minus 9. That's not minus 3, is it? Here we have 9 and minus 9. That's 0. That doesn't work either. Here we have 1, and that's certainly not 10 to the minus 3. Here we have 10 to the 9th and 10 to the minus 12. We add those, we get minus 3. Remember, when you convert these things, the exponents simply add. If you have trouble with that, I believe that there's a tutorial that even comes before chapter 1 on adding exponents. I feel bad for bumming Lake Michigan because actually it doesn't have much mercury in it at all. Most of it's in the ocean. But in this thing we have a concentration in a 1 liter sample is found to be 1 times 10 to the minus 11 molar. So, which is true about our sample? Does it contain 10 to the minus 13 moles of mercury? 10 to the minus 9 moles of mercury? 10 to the 11th? Or 10 to the minus 11? Or do you need to know the volume of Lake Michigan? Well, no, you don't need to know the volume. Think about it. This is 10 to the minus 11 moles per liter, isn't it? What volume do we have? 1 liter. Therefore, it's 10 to the, ignore that. 10 to the minus 11 moles. I put it in the wrong spot. That's an oops. Converting Celsius and Kelvin. We remember that centigrade plus 273 is Kelvin. We have something here in Kelvin. So what's going to be Kelvin minus 273, right? This is minus 269 centigrade. Centigrade plus 273 is Kelvin. On the final exam, you do get to bring all 4 of your little 3x5 cards, okay? So, if you still have them, you should probably save them forever. Isotope of iodine, mass number is 131, is used in cancer treatment. How many protons are there in this isotope?
78.
Remember back in chapter 1 again. Number of protons gives us what? That's the atomic number. That's how the periodic table is arranged. So if I say the atomic number is 53, it has 53 protons. Doesn't matter what the mass is. Anything, 53 protons is an iodine. Oh, we all love the balance equations. There are several ways you can do balancing on multiple choice exams. This is one of them. Here I want you to balance all these things and then come up with the sum of the coefficients. So, we start here with 7 carbons. let's just say that, for starters anyway, we're going to get 7 CO2s. All right, we have 10 hydrogens. How many waters would that be?
5.
5 waters.
Now we
Now, how many oxygens are on this side? That's 14 plus 5, 19, right? But our compound here has 3. So we're down to 16. How many O2s do we need? We need 8 of them. Add it all together, our coefficients come to 20. Now the other way we can do it is to give you an equation and say, what's the coefficient for somebody? But you still have to balance it. Well, I would start at the beginning here again with my potassium dichromate. I have 2 potassiums, so I'm going to get at least 2 KIs. One of these, 2 KIs. I have 2 chromiums here, so I'm going to get at least 2 chromium triiodides. I have 7 oxygens, so I'm going to get at least 7 waters. If I have 7 waters, how many HIs do I need?
14.
14. Now let's add it all up. I have 14 iodines here. I have 6 here. I have 2 here.
8.
What do I need? I need 3 I2s. Started off with 14 iodines. Use up 6, 7, 8. So we need 6 more, 3 I2s. All right, once again, this one is designed to make you nuts. It's a simple stoichiometry problem. Think about it as a simple stoichiometry problem. We are trying to find the number of moles of iron 3 chloride. We are given here that we have 4 moles of chlorine. Okay? So we're trying to find X moles of iron 3 chloride. What's our algorithm? Given and a ratio, right? Our given here is going to be the fact that we have 4 moles of chlorine.
So we have to do 2 times
Now in our ratio, the units of given must be in the denominator, right? So as we look at our stoichiometry here, between chlorine and FeCl3, moles of chlorine must be in our denominator. So 3 moles of chlorine for every 2 moles of iron 3 chloride. Moles of chlorine will cancel. And so what do we do here? We multiply 4 moles of chlorine by 2/3, not 3/2, none of the above. Set up your given, set up your ratio, find your simple stoichiometry ratio here. All right, we have a complicated equation here. This is ethane, has a molar mass of 30 grams per mole. We are given here that we have 30 grams of ethane. That's 1 mole, right?
But in the equation,
Now, for every ethane, how many oxygens does it take? 2 moles requires 7, right? If 2 moles require 7, 1 mole is 3.5. Lewis dot structures. Which one of these guys is long? Now, we don't have a decent periodic table here. Germanium. If you had a periodic table, which you will, you would see that it's in group 4. So we should have 4 valence electrons. Fluorine, of course, is in group 7. So it has 7. Silicon is also group 4. It has 4. Sodium, group 1, has 1, but 4. Nitrogen here is group 5,
it's got 6.
and it's got 6.
They,
Which one of these guys would have the fewest number of electrons in a properly drawn Lewis structure? All you're doing here is you're saying which one of these is in the smallest group number, right? Lithium is group 1. Gallium here is in group 3. Bromine 7. Selenium is 6. Calcium is 2. Lithium, group 1, 1 electron. Now this is a nicer Lewis problem. We're looking for the correct Lewis structure for chlorous acid. Simplest, well, there are lots of ways to do this. Hydrogen is group 1, chlorine is group 7, oxygen is group 6. We sum up all of the valence electrons. Our structure, to be proper, must have 26 electrons. All right, so that's step 1. Now we just look at them and we say, well, this is silly or whatever. This first guy, chlorine has 2, 4, 6 electrons around it. It's not going to be happy with that, is it? So we can rule it out. Here our chlorine has 2, 4, 6, 8, 10. So does this oxygen. That's really unhappy. We can rule that one out. Here we have 2, 4, 6, 8 on everything except hydrogen. And that's good. So this one's still a possibility. 2, 4, 6, 8, 10 on the oxygen. Forget that. And the same thing here. Let's just confirm that we have 26 electrons. So we have 6, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Those come out right. And number 3 is our proper structure. All right, this is kind of a limiting reactant problem without a whole lot of calculations involved. we're dealing with trisilicon tetranitride. We're making this from 0.62 moles of nitrogen, 0.74 moles of silicon. Simple synthesis reaction. Is it redox? Of course it is. All right. For every 3 silicons, we need 2 nitrogens. You can look at this and say, we are given here that we have 0.75 moles of silicon. Right? So for every 3 silicons, you need 2 nitrogens. So how much nitrogen will we need for our 0.75? We need 0.5. 3 to 2. How much do we have? 0.62. So we got lots of this stuff. We're just going to look at our 0.75 moles. Now, for every 3 silicons, we get 1 of these guys. Correct? So if we have 0.75 here, we get 1/3 amount here, or 0.25. It is a limiting reactant problem, but the numbers are very straightforward, and so are the calculations. Three grams of calcium react with excess fluorine. How many moles of calcium fluoride do we get? Well, what's our stoichiometry between calcium and calcium fluoride?
1 to 1.
It's 1 to 1, right? So if we have 1 mole of calcium, we get 1 mole of this stuff. All we have to do is figure out how many moles of calcium we have. And how do we do that? Mass divided by molar mass is moles. So we take our 3 grams divided by 40, and that's 0.0749 moles. 1 to 1 ratio. We have 91 grams of magnesium chloride in 2 liters of solution. What's our concentration? We need to know how many moles of magnesium chloride we have, right? And how do we do that? Mass divided by molar mass. 91 divided by 95, that's about 0.96 moles, right? We have this in 2 liters. So moles divided by liters, 0.48 moles per liter. All right, very simple titration here. We're looking for a volume of 0.18 molar HCl. We have 0.395 grams of magnesium hydroxide. We need to know how many moles that is, correct? So we're going to do mass divided by molar mass, and that will give us moles of magnesium hydroxide. We have 0.0068 moles of magnesium hydroxide. Now, it takes 2 moles of HCl to react with every one of these, right? So we're going to need twice as many moles.
So times 2.
So we're going to multiply this guy by 2, and that's going to give us moles of HCl. Now we know moles per liter, therefore, multiply this by 2, divide it by moles per liter, and we have 0.0736 liters, which is 73 mils. Only thing you really have to remember on this one is 2 HCl's for every magnesium hydroxide. HCl dissolves in water, right? When it does, what does it do? Totally dissociates into hydronium and chloride. 1 HCl gives 1 hydronium and 1 chloride. Okay, we have 0.02 moles of HCl in 50 mils of water. We can do moles per liter, and we can get a concentration, can't we? Now this question asks chloride and hydronium. The thing you have to note here is that the 2 must be equal. Because 1 HCl gives 1 hydronium, 1 chloride. They have to be the same concentration. So all you do is take your moles divided by liters, and this is 0.4 moles per liter for both of them. It must be the same. Moles divided by liter is molar. Oxalic acid. Don't even have to draw the structure of oxalic acid, do we? C₂H₂O₂. We're looking for the conjugate base. Now what happens when an acid forms its conjugate base? It's going to lose a proton and a positive charge. So we're looking for one of these that has 1 fewer proton and 1 less positive charge. Now this is neutral, so when we lose a plus, it's going to be minus. This is H2, this is H, minus C is the proper compound. Loses a proton, loses 1 positive charge. We have sodium hydroxide. In this solution, the hydronium ion concentration is 10 to the minus 12 molar. What is its pH? pH is simply going to be minus log hydronium, isn't it? Remember how to do that. Type in the hydronium ion concentration on your calculator. Hit the log button. Change the sign. This is 11.2. Lemon juice is acidic. The hydroxide ion concentration is 2 times 10 to the minus 12. What is our pH? Now Now, if we're given a hydroxide ion concentration, we can easily get a pOH value, can't we? Because we know minus log hydroxide gives us pOH. Just like minus log hydronium gave us pH. So our pH here is 11, or pOH is 11.7. Now we want the pH, don't we? We also remember pH and pOH must always be 14, so we subtract them. We're at 2.3. One more. Here we have water with a hydronium of 10 to the minus 9. What's the hydroxide ion concentration? Now you can do this two ways. You can convert that to a pH, get a pOH, do 10 to the minus pOH, and you can get that. Or you could simply remember, hydronium times hydroxide is always 10 to the minus 14. So here we are given hydronium, that's this. We remember 10 to the minus 14, simply do our division. We're looking for 10 to the minus 5, which isn't there. Any valid chemical equation, numbers and types of elements must be the same on both sides. We can't do magic, therefore we must have the same numbers and types. Total number of atoms on each side must be the same. Actually, if you think about number 1, this has to be correct, doesn't it? Have to be the same number of atoms, and they have to be the same numbers and types. And the mass must be the same. Mass of reactants must equal mass of products. That was Lavoisier. All of these are correct responses. And our last one here. We are looking at the reverse reaction. So we're starting here, going backwards. In the reverse reaction, which compound is our Bronsted acid? What does an acid do? It donates a proton, right? So in our reverse reaction here, who is donating the proton?
H3O.
Hydronium. Now what I just told you about how quickly you're going to be able to do your final exam, we did this in about 30 minutes, and that's because I talked too much. Right? Once again, remember it's on Wednesday. I think it's going to be over there, but if it's not, we'll do it here, or we'll do it in the hall, or we'll do it somewhere. All right? Remember, exam number 4 is now online. That's chapter 9. Your final exam will look a lot like this. Not a lot of chapter 9 stuff. Good luck. Yeah.